Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course. And as always, it is an honor and a privilege to be serving you, as it is every day, in my virtual classroom with some basketball footage behind me right here. This is, the All-Star game? So, okay, I'm going to get started here. I haven't been here for a while. Long time no see. Couple weeks. I've been teaching my students a couple things they've already learned before, so isn't that kind of weird? No, I was doing things with word problems in equations, systems of equations. We've done those before, and we just set them up. So today, what we're going to do is we're going to be looking at actually graphing linear inequalities. We've graphed linear equations before out of standard form and slope-intercept form and things of that nature. So today, what we're going to be doing is graphing linear inequalities with two variables. I've graphed inequalities with one variable for, on a number line where we have the open circle and we go to the right or left, something like that. Two variables is different. We have a two variable plane. We'll talk about shading regions. If you've done this before, cool. You're here still to learn something though, so I'm here to teach you it. So without further ado, I have 8 practice problems to do. I'm going to try and really just do them one way each, but each way will be different per problem maybe. It depends on what's best for it, and I'll explain it for the first time that I do a certain way and just jump right into it there. All right, so I'm going to go ahead and get started with you guys here. I'm hungry. I got some food I want to eat. Let's get started. So we're going to graph inequalities. All of them is the same instruction. We're graphing them all, finding the shaded regions and the graph axes and all that. Okay, so the very first thing that I'm going to do with each and every problem is, I know this says greater than or equal to. I know this says less than or equal to. For the time being, I'm going to play under the assumption that it just says equal to. And the reason is because I don't necessarily need to be distracted by what the greater than or equal to does, because I'm not using the greater than portion yet. I'm really just using this equal to. First thing I'm going to do is I'm going to graph this line. And I'm going to use the standard form version, hide and divide, to go ahead and do these here. If I set y equal to 0, I can find my x-intercept. 4x equals 28, therefore x equals 7. If x equals 7, that's my x-intercept right there. If I set x equal to 0, I get my y-intercept here. Negative 4y equals 28, so y equals negative 7 if I divide by negative 4. Again, this is something that you would have done before with me or somebody else. If you haven't done this before, find your other way to graph this thing. That's totally fine. I dig it. Do whatever you need to get your graph in. But ultimately, your graph should end up looking like this right here. A line that goes through these 2 points, right there. A line that goes through those 2 points, and there it is. Now, just so you know, as I said, I turned this into an equals because this line is important for every graph that we do. You can still make a line within these, and we're going to make that happen. Just like when we solve those other x things, if I had x minus 3 is less than or equal to 8 right here, I add 3, I get x is less than or equal to 11. We do it like it's an equal sign. X minus 3 equals 8, add 3, x equals 11. The 11 still matters because it's our boundary point that we use to end up going to the right or left with things. Same thing here. What we're going to do, though, instead, we don't have a boundary point. What we have is called a boundary line. And the boundary line, remember, it extends forever in these directions right here. Forever. That's what the arrows tell you. And what it does is it separates what's above it from what's below it. And I'm specifically saying above and below. I'm not saying left and right. Yes, this may look like left to you, but really we're talking about above versus below. In certain respects, you'll see what I mean when we actually do talk about them. But shading one region or the other is dependent upon the greater than versus different signs, things like that. Okay, so I graphed a boundary line, and the boundary line was used. I'm going to go ahead and check that off. I got that taken care of. Now I'm going to use the greater than in a bit by talking about what we're actually going to be doing here. Remember, I'm doing this out of standard form in this particular equation. Looking back at the equals for a second, when I graphed this line, when I graphed this function, what I did was I made a line that represents all the different points that can be a solution to this equation. All the ones up and down this here. What I mean is, if I plug in a certain value for x and y, such as 9, 2, when I plug these in, 4 times 9 and then 4 times 2, I get something that actually makes the left side equal the right side. Every point on this graph will satisfy this equation. That's why we draw the line. There's an infinite number of solutions that goes up and down here. When we do greater than or equal to, however, instead of just equal to, these aren't the only points that matter anymore. The points on the boundary lines aren't the only ones. What I need to do is find x, y values that when I substitute them, the left side is greater than the right side. It can be equal to as well, but I'm talking specifically on the greater than portion. That when I substitute something on the left side, I make it greater than the right side. See, if I plug in some values for x and y and I get 20, 20 sure ain't greater than or equal to 28, so that's not going to work there. So if I plug in something and I have that, that's a problem for me. So let me tell you this about shading regions. I'm either going to be shading the region up, hang on, let me thicken this and make it faint. I'm either going to be shading the region up here, or I'm going to be shading the region down here. Which one is based on doing a single point test. I'm going to do a single point test. What I mean by that is I'm going to choose a point on my graph. I'm going to substitute it into my inequality. And if the left side ends up being greater than or equal to the right side, then that means that that particular point is not only a solution to my inequality, but every point in that same region, meaning on that side of the line, is also going to be a solution to my inequality. Assuming I drew my boundary line correctly and assuming that I tested that point correctly. And I'll show you a very easy point to test, and I hope it works for almost all these problems here, if not all of them. I'm going to test the point 0, 0. I'm going to test the point 0, 0 because it is mathematically impossible to compute incorrectly. I'll show you what I mean by this. 0, 0 is this point right here. Now remember, if 0, 0 ends up satisfying this inequality, then that means everything on this side will. And all that shading means, just like a line, all that shading means is it's a way of covering everything on here instead of putting point, 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 point. I don't want to do a bunch of points over and over. We'll just shade it. So I'm going to test 0, 0 with this inequality, and I'll see if I make a true statement. If I make a true statement, I'm going to shade on this side. If I make a false statement, that means 0, 0 doesn't work. That means none of these work. That means these points work. And I'll shade on this side. And I'll double check it if it's, wrong with that. All right, why am I choosing 0, 0? You know what 4 times 0 is? Do you know what negative 4 times 0 is? Yeah, they're both 0. Do you know what 0 plus 0 is? It's 0. You know what happens here? I don't got to compute nothing. I just turn it into a big fat goose egg. 0 is greater than or equal to 28 is the statement that I end up making here. Now, is 0 greater than 28? No. Is 0 equal to 28? No. So this became a false statement when I substituted 0 for x and 0 for y. A false statement means that 0, 0 is not a solution to this inequality, which means nothing on this side is a solution to this inequality, which means everything on this side should be a solution to the inequality. So I'm going to go ahead and I'm going to shade on z. I'm not going to say on the right side. I'm going to shade underneath the line here. I got to be very careful and not compare left versus right. It's all about top versus bottom. You'll see what I mean when I do another problem here. So this shaded region right here, I feel like it's supposed to be blue. What just happened? Whatever. This shaded region right here is the solution set for all these. And let's make sure one of them work. I'm not going to do this for any other problem with this one. Let's try an easy one like 9, 0 right here. 4 times 9 minus 4 times 0 is greater than or equal to 28. That is 36 minus 0 is greater than or equal to 28. 36 greater than or equal to 28, that checks out. So that checks out, so everything else on this thing will check out as well. All that they're asking you to do, though, is graph the inequality. And you need two things, the boundary line and the shaded region. And that's it. Okay. This test helped me generate a shaded region because I used standard form. All right. Okay, second problem here. I am going to use standard form one more time because I did seep through the problems and it looks like standard form is not used very much. I can use standard, what I mean by that is I'm going to graph out of standard form because I can divide 12 by 3 and I can get 4. That's my x-intercept. And then my y-intercept, I can divide 2. Excuse me, I can divide 12 by 2 and I'll get 6. These 2 points make a line, and I'm going to go ahead and draw that line for you. This is the boundary line for this equation right here. There we go. Sorry, I have to kind of get it perfect, otherwise it doesn't work. All right, so that's my boundary line for this one as well. Okay, so let's repeat what we did last time. This is the boundary line. I did it as if I graphed it if it was equal to. I graphed it as if it was equal to. Now we're going to talk about less than or equal to. I'm going to go ahead and test the point 0, 0 again. 0, 0. Now, I don't have to draw this point each time. I'm just making sure that you understand that I'm color coding this for a reason. 0, remember I plug in 0, is less than or equal to 12. That is a true statement. 0 is less than or equal to 12. What that means is that 0, 0 is a solution to my inequality, which means everything, 1, 2, or -6, -10. These are solutions by inequality as well. Anything that is underneath this line. And remember, this line goes forever. So even up here, underneath it would satisfy it. I'm only going to fit the ones that I can within the grid marks though. So let's go ahead and draw out that shaded region. You can just lightly shade if you're drawing, because I'm obviously using a tool here. I can't really do a light shade on this like with a pencil sketch kind of thing. So that's my shaded region right there. This one did check out, remember. That means all of them here checked out. And that's the graph. So what I just did in these last two problems here, because I imagine I'm going to go into slope-intercept form here. What I did in these last two graphs is they were in standard form. I graphed out a standard form. That's not a requirement, but I did. I graphed out a standard form. What's nice about not graphing out a standard form, but what's nice about using the graphing inequality, graphing the inequality out of standard form is that 0, 0 test. Because that left side just becomes 0 and it's clean. Now, if you're in slope-intercept form, one side becomes 0. It's not bad in that form either. It's just that in standard form, it's clear as day what you're going to put. That's all I'm just saying there. What else was I going to say to this? I have it. Hang on. I got it. I don't remember what I was about to say here. Oh, here's what I was going to say. If your line does cross through the origin, though, let's say the graph looks like this, 0, 0 is not a value I can test. I can test it, but that's going to be a question of whether the line is a solution to it. We need to know which region is a solution. So if my line looks like this, I can't test 0, 0, but I can test 0, 1 or 1, 0 or something like that, or 1, 1. I'm just saying 0, 0 is really easy, and I would test it as long as it's inside one of the regions, not on the line itself. Okay. All right, moving on. Okay, the third problem right here, y is less than or equal to 3. Kind of interesting kind of problem because there is no x here. It's kind of in slope-intercept form-ish. I'm going to change it to y equals 3 so you see it in a different format. This is y equals 0x plus 3. Okay, this is y equals 0x plus 3. You know, you can't see it. That means a 0 is your slope. If I have a 0 slope, that means I have a horizontal flat line. Y equals 3 is the line that goes forever left and right, okay, on 3, like this. And you might think, what about going up and down? Well, no, y, I went up from here, 1, 2, 3, and these are all the y equals 3 values. Here's 2, 3, here's 9, 3, things like that. Here's y equals 3. Okay, here's y equals 3. Now, we need y is less than or equal to 3. Okay, this is the first problem that we're going to do that is kind of slope-intercept form-esque. Remember, I mentioned it like this. Treat it like it's slope-intercept form. Okay, here's my inequality less than. Here's all I want to say about it, and it's going to make more sense when I do another slope-intercept form thing as well. Here's some value y. Here is some value x that gives us some other value y right here. What we're comparing is the y that we create here to the y that is created as a result of what we plug in for x here. We're comparing one y to the other. Remember, this y comes as a result of plugging in this x. This y comes as a result of a point that we choose. So, for example, let's say, and this example is not great because there's 0, but let's just go along with it. Let's say I plugged in the point 3, -1. I want to see if I get a true or false statement here. And look, I can do it right here as well because the 0, but I just want to use it with the x thing to make sense of that I'm plugging it into x. I substitute 3 in for x. I get 0 times 3 plus 3. I plug in -1 for y, and I get that. 0 times 3 is 0, and that's why it turns into that 3. 0 plus 3 is 3, that's why it turns into 3. -1 is less than or equal to 3. That's actually a true statement. Remember, it doesn't have to be equal to the thing. It can be less than or equal, which means it could be equal. This is a true statement. That means that everything else under the line is a true statement. Cool. And I am going to shade, and that's correct. It is correct. Now, before I do, I'm just going to make a big, bold, bad statement right here. And this is for all y equals mx plus b's. Well, not equal, but right here, whatever it is, the inequality, I could have greater than, less than, greater than or equal to, or less than or equal to. If I have a greater than, in slope-intercept form, if I have a greater than, a y is greater than, remember, I am comparing some y. I'm comparing some y to this other y that's obtained. If I have a greater than, I'm going to shade above the line. If I have a less than, I'm going to shade below the line. This was a less than. It's less than or equal to, but it's a less than. That means I'm going to shade below the line right here. That's what this problem is going to do. I'm going to shade below because it's a less than. That's what's great about slope-intercept form. You either shade, there's no point you have to test. If you're only comparing a single variable such as y to your thing, then you are either going to shade above the line or below the line. Remember, it's not about left or right. It's about above versus below when you're comparing y to something there. And there is my graph. All right, 5x minus y is greater than or equal to 4. Now, I realize this is in standard form. However, getting this x-intercept isn't great because I got to divide 4 by 5. I know what the number is, but the line isn't going to be fantabulous. We might as well get this in slope-intercept form. Let's treat it. I'm going to keep the greater than or equals to here this time. I'm going to rewrite it in slope-intercept form here. Subtract 5x from both sides, and I'm going to get negative y is greater than or equal to negative 5x plus 4. Divide both sides by negative 1, and when you divide, that means every term divides by negative 1. And I'm going to get, over here, y. When I divide by a negative, I flip the inequality. Y is less than or equal to 5x minus 4. And that's a turnoff for a lot of people when it comes to graphing in slope-intercept form. And I understand when you might have that consideration of saying, maybe I should do it another way. Maybe I should try standard form. A lot of people will forget to flip that thing. When you divide or multiply by a negative number, you flip the inequality. That's why I said I wanted to keep the inequality there that time. And that's why you still might want to test points to see if you're doing it correctly or not. Regardless, this is the line that I'm going to graph, the y equals 5x minus 4. I'm going to graph that. Let's do it how we normally would. We would start from the y-intercept of negative 4, and I'm going to go ahead and rise 5 and run 1, like so. Rise 5, run 1, and fall 5, run 1 to the left right there. And I'm going to go ahead and graph this boundary line. Give me that same color I was just using right here. And it's going to look something like that. Okay, there's my boundary line. Now, there is a stark divide between there's above and below and left and right. Remember, we're not comparing left and right. We're comparing y's. We're comparing y's to other y's right here. We're saying what's above the other. So, y is less than. If it's less than, we shade below. What does shading below the line mean? Well, this is below the line right here. Remember, this line goes forever. This line goes forever. I'm going to shade below the line, which to you might mean shading to the right, but trust me, this is below. Okay? I'm not going to have a perfect shading here. I'm just going to go ahead and whoop. This tool is kind of strange. Shading below the line right there, and there it is. That's my inequality. That's my thing. So you've seen 2 in slope-intercept form, 2 in standard form. I think the majority of them from here on out go in slope-intercept form. I'm hoping to find one that is not, I didn't check on this. I'm hoping to find a problem that's not also equal to, that's maybe just less than or just greater than. So we'll see if we run into that right now. Hooray, we do. Okay, good. So only things I have to teach from here on out is make sure you get into a form, and then also what does it mean if it's not equal to. So this is a mess. I don't see a need to put this in standard form only to maybe find out that it's not a good standard form graph. So I'm going to go ahead and put it in slope-intercept form. I'm going to put it in slope-intercept form, and all I need to do is I need to combine these like terms right here, the 4y and the minus y. That becomes 3y. I need to subtract the 3x over right here, and that is greater than, that's negative 9x plus 12, and I get to divide everything by 3. And I'm going to get y. It looks like standard form wouldn't have been good here. I don't think I'm going to get a integer x-intercept. Divide everything by 3. I'm going to get y is greater than negative 3x plus 4. Yeah, this would have not worked for standard form. Okay, y is greater than negative 3x plus 4. What I'm going to do is I'm going to graph this boundary line like as if it were equals, and then I'm going to shade above because it's greater than. Now, there's one thing with this line that's going to be a little different, and it has to do with the fact that it's greater than, not greater than, or equal to. But let's start with the idea of the line. Let's start with some points here. 0, 4, down 3 over 1, down 3 over 1, etc. Now, the one difference here is your line is no longer going to be solidly connected. What I mean by that, when I draw this line here, it is actually, instead of looking like this, and you can start by drawing this and get your eraser out, but instead of looking like this, I'm going to go ahead and make it look broken like this right here. It is a dashed line. It is a no longer solid. Okay, so you can either draw it straight up. I'm not going to do that here. I'm just going to use this tool. You can draw it straight up, but with the dashed line is to planes like the open circle is to number lines. So remember again, x is greater than 11 or whatever I put last time. 0, here's 11. I'm going to put an open circle on that and go over here. Whereas if it was greater than or equal to, it would be a closed circle, right? The open circle, the greater than and less than or whatever, the dashed line here is like the open circle here. It's a way of saying that if I choose a point that is on this line, it actually doesn't work for the inequality. Let's try 1 and then we'll stick to it from there. We'll leave it at that. This is the point -1, 7. I'm going to substitute -1 for x and 7 for y in the original inequality that's up here. And what you're going to see, well, you'll see what you're going to see, but you'll realize why this doesn't work here, but it does work for a greater than or equal to. So we got 4 times 7, which is 28. 3 times -1 is -3. Minus 7 is greater than -6 times -1 is 6 plus 12. 28 minus 3 is 25. 25 minus 7 is 18. 6 plus 12 is 18. I'm going to make a statement that says 18 is greater than 18. 18 is not greater than 18. It happens to be equal to it, so that doesn't work. That means any point on this line will not work, but the ones that are above will. I'm still going to shade above. I have to do that. Why would this work if this was greater than or equal to? 18 is not greater than 18. But it's equal to 18, and that's what this part's saying right here. It says greater than or equal to. I can only satisfy one of them. I can't satisfy both. I can't be greater than and equal to my number. I'm either greater than it or I'm equal to it. And greater than or equal to actually seems to work out. So that means that point would work. That's why we draw a solid line on those ones. So the solid line, again, is the emphasis of saying the boundary line in itself is actually a part of your solution set. A dashed line says this boundary line is not a part of your solution set, and that's why we draw the dashed line for that. Okay, I still have to shade above. I'm going to go and do that right now. The greater than means shade above, and again, above the line is over here. This is above the line. It doesn't have to do with right or left. I'm going to keep emphasizing that. There's no reason not to. So shading above the line like so, and this is my solution set. You can still do your 0, 0 tests. I imagine at some point I should do one. You know what, 0, 0 is not a bad test with this one. Let's make everything go away. Check this out. Let's test 0, 0. By the way, when I test 0, 0, I expect a false statement because 0, 0 is not on the region that's shaded. Okay, see the shaded region is over here. So let's test 0, 0. 0, 0, 0, 0 is greater than 0, 12. Is 0 greater than 12? 0 is not greater than 12. Therefore, this is not a solution. Neither is anything that's on this side of the inequality of the boundary line right here. Only these things are. So you can still test 0, 0 things like that, but this is the above below thing I want to talk about as well. All right, next problem here. I think this is the 6th problem. Ready for slope-intercept form if we divide everything by -15. You mind if I just do that straight up? And remember, we do divide by a negative. That means the inequality is going to flip. Let's use a different color. I'm getting blue color blind here. Let's go back to purple. We get y is less than, remember flip it, -2x plus 3. And look, I imagine the majority of your things are going to be in slope-intercept form. Not saying that as a certain, but I imagine a lot of people are going to want to convert in slope-intercept form anyway. So don't be too upset if I do too many in slope-intercept form the rest of the way. I feel like they're geared for it. These other ones are not for standard form. You can test 0, 0. Keep testing 0, 0. All right, -2x plus 3. Start at 3 and go down 2 over 1. This problem's a lot like the last one as far as the graph looks. However, the shaded region, I'm seeing a less than now. Right? I'm seeing a less than, and a less than would mean shade under. Now I'm going to test 0, 0 for you and make sure that shade under does work. Now my line, if you recall, is going to be a dashed or a broken line here because we are doing less than and not less than or equal to. So dashed or broken line as the boundary line in itself. Okay, that's the start. And then after that, I'm going to go ahead and do my shading. Now I anticipate I should be shading underneath. Underneath is here, which by the way includes 0, 0. When I plug in 0 for x and 0 for y, do I get a statement that works? 0 is less than 3. That works. That means 0, 0 is a solution. That means everything underneath alongside 0, 0 is also a solution. So hopefully you're getting the hang of this. There are only 2 more that I have to do. They're a lot like these ones here. Of course, I probably got to do some problem rewrites or who knows what. But shading underneath right here is the way that I go about that one. Now, by the way, what's this going to lead to? Because I've been teaching systems for the past, month at least, month and change, right? A lot of systems of equations. We're going to get into systems of inequalities. We're going to get into systems of inequalities where you graph 2 together on the same thing. That'll probably be my next video. And then we're going to be doing some word problems with systems of inequalities as well. So you'll get at least 2 more videos outside of this one when it comes to teaching you some of the things with practice problems. And then I'm going to have a review video that's covering all of that in whole. Okay. All right, 2 more problems to do, and then I am done. I'll hit nearly around that 30-minute mark. Once again, standard form is written, but I don't like the idea of standard form because I don't want to have to divide by 10, 36 by 10, and get 3.6, whatever. Let's just go into slope-intercept form, and I'm fine with fractions for my slope. Subtract 10 from both sides. I get negative 6y is greater than negative 10x minus 36. Divide everything by negative 6. Negative 6, negative 6, negative 6. Again, dividing by a negative, flip the inequality. At some point, you're going to mess up on not flipping that inequality. And as long as you test a point to make sure that it works, there won't be a problem because you'll know to flip it afterward. So remember to flip your inequalities, remember to test points as often as you're able to. Okay, I reduced 10 over 6 to 5 over 3. I divided the 10 by 2 and the 6 by 2 and I gave a better looking version. Everything was negative, divide by negative, everything is now positive. So y is less than 5/3 x plus 6. Let's go ahead and do this in black. Why not? Start at 6, rise 5, run 3. Not really on the graph, but that's okay. Down 5, left 3 over here. I can fit a couple of these, it looks like. I hope that's on the same line there. I think so. And once again, so it looks like the last 4 problems that we did were all broken lines and the first 4 were all solid lines. So you don't get interweaving practice, but you heard it, you can do it, all's gravy. All right, there's my boundary broken line to indicate the difference between one side and the other. I'm shading underneath the line because y is less than. And again, notice, in standard form, it was not less than. So I can't just say I'm going to do it based on this. It really has to do with whether y is negative or positive, but I don't want to talk about that too much. Y is less than right here, so we will be shading below this line, okay? And in shading below the line, we're going to have something like this. 0, 0 should work in the, by the way, always test the original inequality when you do something like this. But 0, 0 should make a true statement in the original inequality. That's what standard form is good for again. Is 0 greater than negative 36? Yep. Therefore, this is a solution. Therefore, these are all solutions. Okay, last problem. 7x plus 2y is less than 2. Once again, I can't divide 2 by 7 and be happy with it. I am going to go in slope-intercept form. That's why I was very fine doing standard form for the first couple. But I can test that 0, 0 thing. In fact, let's test it right now. 0 is less than 2. So when I test 0, 0, whatever side has 0 should be the one that I shade on because I made a true statement out of plugging in 0, 0. So interesting. Anyway, slope-intercept form. Subtract 7x, 2y is less than negative 7x plus 2, and divide by 2, y is less than negative 7 halves, x plus 1. Again, dividing by 2. I want to do this one pretty fast here. Down 7, right 2. Can't really fit anything else there. Up 7, left 2. And let's go ahead. It is a dashed line, is a broken line because of the less than. And now this 0, 0 is very close. Look at this. This 0, 0 is very close to being on that boundary line. It's not. In fact, it's underneath it. And 0, 0 gave us a true statement, if you recall. It gave us a true statement, therefore everything on this side of the boundary line will be. And you don't want to call it the left side. It's not about left when you're comparing y. It's about under. Less than, under. I am shading under this line. Remember, the line does go forever. So this is considered under as well. This is all over. So I'm going to shade under the line. Let's go ahead and do that last one. And then I am finished. And then you are finished. And then we are finished. So let's go ahead and do that last bit of shading. Remember, the shading just means all of these points are solutions. This is the fast way of doing that. The boundary line being dashed means points on the line are not solutions, but solid means points on the line are solutions. All right, so that will do it for this one right here. A good half hour of work. My name is Mr. Robinson. Next time you see me, we'll be graphing systems of inequalities. It'll be more of the same, only we're going to be graphing two on the same graph. So make sure you're practicing drawing and shading lightly and doing like going against the grain, things like that, because I'll be trying to do those practices when I do systems of inequalities. It sure to work out. All right, thanks for watching and see you next time.